Hello everyone, I'm Sarthak, and this is my video submission for the assignment given by Valura AI for the AI engineer role. For this assignment, I was given the task of building an AI microservice for a financial company, which included multiple layers, such that the safety layer, the classifier layer, the agent layer, and at the end of the whole thing, there was a fast API endpoint where the user can insert their queries and they will receive uh, outputs through a server-side event technique. So this video consists of three sections. First of all, the first one is the architecture, where I will explain the architecture of the project that I did. Second one is the answer to the most unobvious thing that I have done in this project. And the third one, what would I do if I am given 1 week extra in this project? So this is, I've also inserted a time span so that you can go to those sections if you want. So yeah, now I will start with the section of the architecture. So I hope you like this video. Thank you. So firstly, I would explain the architecture in a nutshell. So the system starts with a fast safety guard that runs locally using regex only to block harmful financial requests before any AI is used. If the query is safe, it goes to the classifier, where first the regex rules try to resolve simple queries. So about 30% of the queries don't even need any LLM calls. For the remaining queries, a single model calls returns a structured JSON that the router uses to load the correct agent. I will explain the architecture in more detail when I will go through each step individually. So the agent that was focus of this assignment, which was the portfolio health, combines deterministic risk calculations, an LLM explanation layer, and a hard-coded compliance disclaimer. So after all of this, the final response is streamed to the client in real time, and any disconnected requests are cancelled to avoid wasted API costs. So the first layer of this pipeline is the safety guard. And one of the requirements of this layer in the assignment was it has to run in under 10 milliseconds. So it ruled out any kind of LLM classification or any semantic based classification. So this layer is completely Python based with no networks and no other dependencies. So it has three steps. The number one is clean the input, lowercase, remove punctuation, and normalize white space to so that something like this becomes something like this. The second step is detect the topic. So we can scan for phrases across the categories that were given in the assignment, which include money laundering, insider trading, etc. So it can be done using the simple substring matching. The third step is score intent. Educational phrases, for example, what is explain, compete with actionable phrases like help me, how do I, and the higher score uh, besides the intent. After that, the rule is risky topic plus actionable intent equals block. Risky topic plus educational intent equals allow. So out of the 22 harmful queries in the testing data, the layer logged all 22 of them. So the next layer of the pipeline is the classifier layer. And since this layer consists of LLM, I have tried to optimize the token cost by implementing a 5-layer cost funnel. Each layer runs only if the previous cannot answer the user query. And every step is faster and cheaper than the next. So these layers are the layer 0, which is to filter out the greeting messages. For example, good morning, hello, and stuff like that. These kind of queries get filtered out by this layer. The sub zero level, which is the pre-classifier layer, which has certain rule sets and certain phrases to identify the most common queries. And I have set a confidence threshold of 0.75, and if the phrases matches and the confidence uh, exceeds the threshold, it returns the agent that is required for that particular query. This is implemented for the most common queries a person can have, and this does not require any kind of API calling. This function is not there for a long conversation history because there it can backfire and it would not route the exact agent. But in the test queries given in the assignment, about 30% of the queries never had to hit the API, basically decreasing the cost by 30%. So let's get into the LLM part. If this does not work, we have the LLM routing, but very so temperature is zero of the model. The max token is 120 tokens, and the history is limited to the last 4 messages. The older context just add noise without improving the routing. I have also talked about this in the most obvious thing that I've done in this project, so more depth into I would get more depth into it in that particular session. So for this, I have used the GPT-4o Mini, which is fast, cheap, and sufficient for deterministic JSON classification. It's not a reasoning task, so this would be enough. So the second layer is the soft repair. Sometimes the JSON format can be a little loose, which leads to bad parsing. So instead of calling the NLM back, we can first try to soft repair it using regex. And by fixing the trailing commas and removing markdowns and stuff like that, and reparse. If that fails, then Then it calls the LLM and the final fallback basically, which is the layer 3. So in this way, the whole architecture works of this layer working perfectly. Okay, so now we will get to the third layer, which is the agent layer. So the target agent of this assignment was the portfolio health agent. So to optimize this agent, I have implemented a three-layer pipeline. Let's talk about each layer. So the layer one is pure Python. So what happens in agentic workflow? We try to fit all the context into the LLM, and then the LLM has to do all the calculations and then interpret that and then tell the user, which takes a lot of tokens and also takes a lot of time and can lead to hallucinations. So instead, I have used Python to do all the calculations first and then use the LLM as a communicator or as a translator of all those calculations. So first layer is pure Python, no network. So for each position, we compute cost basis value, average cost times quantity, sum everything to get a total value, divide each holding to get its weight percentage, then two thresholds. If the top holding exceeds 50%, flag high. If the top three combined exceed 70%, flag warning. Sector exposure is summed the same way, but broad market ETFs and bonds are excluded from sector flagging. They are diversified by nature. Flagging them would be noise. So okay, this was weird, so I would show you some calculations. For example, let's take a user Marcus and 80% NVDA cost basis are 180 shares at 280, so that would be 39,312. Total portfolio 49,249. Weight is 79.8%. Top holding crosses 50%, so flag fire. So yeah, and in this way, all the calculations are done even before any API call is done. Second layer is the LLM layer. So it does not have to do any calculations now. It just have to communicate all these calculations to the user. And in this way, we are not just saving time, we are also saving token usage and decreasing the chance of hallucinations. The third layer is just one line, the disclaimer. As we are working with LLMs, they can be a little unpredictable as we know. So the third layer is just a compliance or just a disclaimer that, okay, it's an LLM. Do not completely trust on it. So that's my third layer in this project. So yeah, this was the agentic layer. Okay, so to answer the most unobvious thing that I've done in this project is in most implementations related to LLMs, people either pass the full history or use a token truncation method when dealing with a chatbot. But I deliberately designed this pipeline in a way so that it only takes up about four exchanges between the AI and the user. And it was not just because to optimize the token usage and to attain token limits, but also the fact that for a routing task, what the user said three exchanges ago almost never changes how we should classify the current query. The three exchanges, the last three exchanges are uh, have enough context and enough intent for that. Beyond that, you are just adding noise and not accuracy. So I I picked the simplest mechanism that gives you 95% of the context value at fraction of tokens spent. Okay, if I were given another week to develop this microservice, the primary enhancement I would be doing is implementing multi-intent orchestration. Just think about it. When a user asks something, it does not mean that a single agent will be able to answer that query um, accurately. For example, if the user asks, check my portfolio health and tell me if I should buy more Apple stock. So it does not take only one agent to answer this correctly. But the current architecture that I have created will only find the most dominant agent for here, and the output it will generate would not be that satisfactory. So if I was given another week, I would try to implement it in a multi-agent orchestration where the classifier would identify multiple agents for a single query if it requires. So if it requires multi agents, so that would be something that I would develop upon if I was given another week. So that answers the question. Thank you.